Welcome to another Ultralight Airplane Design video from the Ultralight Airplane Workshop. In this video, we're going to talk about load distributions on the airplane. The loads that the air is imposing on the airplane, and where those loads are, how big those loads are, and specifically in this video, we're going to look at the loads on the wing, how they're distributed across the wing. In this case, it's called Spanwise load distribution. If you're new to the channel, what we're working on is an ultralight airplane design where ultralight is defined by Federal Aviation Regulations Part 103. And one of the restrictions for Part 103 airplane is that the empty weight has to be less than 254 pounds. Well, we've given ourselves quite a design goal here of trying to make this airplane mostly out of aluminum. And that's pretty hard to do. And the reason it's going to be pretty difficult to use is we're really using fairly standard aluminum airplane construction techniques. We're not using lots of high drag tubes and wires like you would see on a traditional ultralight. And because of that, all the strength of the airplane is going to be internal to the structure of the airplane instead of external, like with wires and a lot of bulky big tubes. And that actually makes the design a little more difficult. It's going to add more weight to the airplane. And that's going to drive the simplification that we're going to do in this video. And speaking of that, for most of the videos so far on the UWS-4, we've been using Dan Raymer's book, Simplified Aircraft Design for Homebuilders. Now, Dan's book doesn't cover any of these load distributions, so we're really not going to be using his book in this video. Although I will introduce you to another book that's really helpful. We're actually on part 11A here, so we're going to have several part 11 videos that are going to be on distributed loads. For example, the next video is going to be the chord-wise distribution on the wing. After that, which will be 11C, we'll be working on the tail. I don't know if that's going to be a C and D or just C by itself. We'll see. Well, let's get to it. Now, just briefly, I want to mention that in the last video that we did here in this design series, we worked on the load factors for what would traditionally be horizontal tail and vertical tail. Except we have an inverted V-tail, so it's a little bit different for us. We also talked about engine and landing loads. So loads that the engine would impart on the airframe and loads that landing would impart on the airplane. And as I mentioned before, we're using a new book to help us a little bit in this video. This is a book by Chris Hines, and his book is called Flying on Your Own Wings. And this is another airplane design book. And Chris's book is just jam-packed with really, really useful information. He put in a whole lot of hand-drawing pictures, there's quite a bit of equations, and he actually goes into quite a bit of detail on the aerodynamics that are applied to an airplane. Now, one of the drawbacks to how much information that is jam-packed in there is that there's not quite as much of explanation for some of the information that's being provided. So occasionally you'll come across something like an equation that's presented, and it takes a little while to figure out exactly what the equation is saying or how to plug information into the equation to get what you want. But even so, I think it's a fantastic book, and I really enjoy looking at it and using it. Now, in the introduction, I was a little bit brief on what a load distribution is. I've got a picture here of the UWS-4 that I did when I was flying it in the X-Plane 11 program, and we're looking at the rear of it. Now, I've calculated a load distribution for this plane using OpenVSP, and I've superimposed it on the airplane here, and that load distribution in the span-wise direction, so that's from one tip to another, is this yellow line that you can see here. Now, this particular distribution is at a pretty high angle of attack, something like 18 degrees, but you can kind of get an idea of what we're talking about here. So the height of the line from right along here is how strong that lift is in that particular spot along the span. So you can see it's pretty level here in the middle and pretty high, and then as you come out to the tip, it starts dropping off. And then it's got this little funny dip here where you have a significant dihedral change on the tip. In fact, just about anywhere you see a dihedral change, you can see a change in that distribution. Now, in the next video, we're actually going to do chord-wise distribution, which would be front to back on the wing at different points along the wing. And the reason we need to know this distribution is we can design the details of our spar, for example, to be as light as possible. For example, if there's more load out here near the tips, that means here where we have to take that bending load, we'd have to make the spar heavier. The spar casts have to be thicker. But if the load is pretty small here and then increases fairly rapidly toward the middle, that means we can make the spar a little bit lighter because the load is in closer to the middle. And we want to make our spar as light as possible. So we really want specifics on what this load distribution is, so we can make that spar match exactly what the distribution is without having any extra material. Okay, so let's continue talking about what we were just talking about. Now, in Dan's book, if this was included in Dan's book, it would still be in the Analyze It section of the preliminary structural sizing on page 97 of Dan's book. And we're going to use loads that we got in the last series, part 10, to come up with some beam, tension, and compression loads. In this case, beam is the spar. And we also need to know the shear loads in the spar. And we're also going to use our distributed loads to figure out the torsion in the skins of the wing. Now remember, this is mostly aluminum airplane, so we have a fairly fully enclosed wing, and the torsion on that wing is going to be carried in the skins. So as I said before, on the wing load distribution, we're going to do span and chordwise loads, and we need to know the loads on the ailerons and the flaps, still using this load distribution, and we need to do the same thing on the tail, on our rotorvators. We need to know what the span, that should be span instead of spanned, and chord. Now we don't really need to do these aerodynamic load distributions on the rest of the airplane. Like the booms that hold the tail to the wing, we don't have to really worry much about load distribution on that. And the fuselage, we're not going to really worry about load distribution on that either. Now, something to keep in mind when we're figuring out this load distribution, the thing that mainly determines the shape of that load distribution on the wing, at least in the span-wise direction, is the plan form in the wing. That's the shape of the wing as you're looking down on it from above. Now we have a rectangular wing with a kind of a little wing extension, kind of like a winglet. But if you had a tapered wing, that's going to have a fairly significantly different shape on that load distribution than on our rectangular wing. Other things that also have some impact on that shape is dihedral. So changes in dihedral mostly. Twist, that'd be like washout on the wing. Frequently on tapered wings, you're going to have the angle of attack on the tip be pointed down a little bit more than near the root, and that's to help keep the tip from stalling before the root does. So that has an impact on the shape of the spanwise load distribution. The shape of the airfoil itself does have a little bit of impact, but not much. And because of that, it's going to impact the method we're going to calculate our load distribution. We can leave out the airfoil except for the camber. Now, as you might guess, it might be kind of complicated to calculate that load distribution, but there are some simple approximations. Now, these approximations don't usually take into account things like the fuselage or nacelles or other things that stick out from the wing. Now, some approximations also are not too good at dealing with dihedral or twist either. Some do, some don't. And these approximations are usually going to be conservative. That means they're probably going to move that lift distribution out a little bit more toward the tip. That way you end up overbuilding your spar. And that's going to make our spar heavier, which we really don't want to have in this ultralight. We're going to have enough problems with weight as it is. Now, Chris Hind's book, Flying on Your Own Wings, does talk about a simplified method for calculating load distribution. We're going to talk about that. And then we're going to use the program OpenVSP, and in there it's VSP Aero program, using the vortex lattice method to calculate the load distribution. And I think in the long run, it's going to be more accurate than most of the approximations that we can use, and I think it's still fairly simple, at least the way we're going to do it. So something I want to mention is the load distribution, this height here, is in units of force per unit length. And that's going to be, for us, pounds per foot. And the per foot is the span. So for example, let's say we want to take this value here, and we're going to say, let's take a 1 foot span of it. So what we can do is we can take that 1 foot multiplied by whatever this value is. Let's say it's 50 pounds per foot. That would end up being 50 pounds of lift on that 1 foot span. If we were averaging over a 2 foot span, then it would have been 100 pounds of lift over that 2 foot span. Now, for the most part, you can do fairly short spans, particularly where there's not a lot of change, a lot of curvature in line. There can be change, but if it's still fairly straight, you can actually do an average. So like from this location here to about here, that's just about 2 feet, maybe 2.5 feet. We could actually just pick the middle value here, multiplied by that 2.5 feet, and for that entire section there, that lift along that section would be that 2.5 times 50, so it'd be 125 pounds along that 2.5 foot section. And of course here in this middle, man, this is almost perfectly flat. And that is what, 7 feet long? So if this was 50 pounds here, that 50 multiplied by 7 would be what, 350 pounds of lift from this center section here. So let's continue. So the simplified calculation for load distribution that Chris talks about in his book is this one. I'm not even going to try to pronounce it. I doubt that I can. But this method is really simple to calculate. So at each span location along your wing, you can get that lift per unit length, and that's what we're talking about here, section lift. You take lift from an elliptical lift distribution. You add a lift distribution that's shaped like the chord, the planform of your wing. You sum those two together, divide by 2. That would give you the average of these. And that will give you that lift at this section. I'm going to do a little diagram here, a picture to show you, and it'll make a little bit more sense, I believe. Now, this approximation is very simple. It's very conservative, which means it moves the lift farther out on the tip so that you end up having to make your spar heavier. It does not take into account twist of the wing. So if you don't have twist, that's perfect. And on rectangular wings, we frequently do not have twist in the wing. And if you're interested in looking at what Chris did, look at page 133 of his book, and you'll see the drawings that he made for that lift distribution. Here what I've done is I've used a spreadsheet to do the calculations for me, and I'm using this shrink. I'm going to take a guess at how to pronounce this. I've used a shrink simplified distribution for the UWS-4. And I've overlaid the various distributions. This red line is the elliptical shaped distribution for lift. This green line is the wing planform shape of the distribution of lift. And then this blue line is the average of those two. For the elliptical shape, this is the formula to use. This is basically just a rearranged version of an elliptical equation where the major axis here is the span, the minor axis is going to be, well, I just realized we have a mistake. Instead of pi divided by 4 up here, this should be 4 divided by pi. Just turn these around. Swap the 4 and the pi. Same thing down here. Swap this 4 and the pi. I'm going to go ahead and do that right now. So we have 4 divided by pi multiplied by the p value. So the average span load is the wing loading. So that's W times N sub 1. Now remember, W is 517 pounds. I've written that down here. N sub 1 is our load factor for the wing, and that's 3.8. Multiply those two together. That's the total weight that the airplane has to handle. And by the way, this is at V sub A, stalling at V sub A speed, and the V sub A speed is 55.7 knots, but that's not part of the calculation here. B is the span of our wing. So the semi-span is 12.1 feet, so the total span is 24.2 feet. And that gives us a span loading of 81 pounds per foot. And again, that foot is along the span. So I did a spreadsheet to do this calculation here. And just as a quick aside, the span location that I've used is the same ones I'm going to use in OpenVSP, and that's going to actually let us compare on a chart, one on top of the other, this shrink distribution and the OpenVSP distribution, which we're going to do here shortly. This planform distribution here in green is basically just the chord of the wing as we move out along the span. So we have a rectangular wing right out here till about 10.5 feet. And then it's just a straight line out here to the tip, and this is about 1.5 feet chord here. So our chord here is 5.18 feet, and out here tip, like I said, 1.5. So basically, I just put the chord in here and multiplied by the average wing loading. And the average wing loading then is our total weight, W times N1 divided by surface area. And then when we take that wing loading, we multiply by the chord, that gives us this height right here. So you can see here at the root, we have quite a bit of difference here in our span loading. It's about 103 here, and it's about 85, if I remember right in here. So now what I would like to try to do is take this average that we came up with, this simplified distribution, and compare it to OpenVSP. Now keep in mind, like I said before, this distribution does not take into account dihedral, it does not take into account the camber of the airfoil, it does not take into account washout or the twist of the wing. And here we're looking at another form of lift distribution. And this is generated by a program called OpenVSP. Now we've talked about OpenVSP in a lot of previous videos. Here is the wing, the pilot cabin or pod, and the booms that hold the tail on the wing. So I ran this through OpenVSP's VSP Aero analysis program and came up with these lines. So we got 3 different lines here. Now as you can see from that picture we were looking at previously, this picture here, that shape should look fairly familiar. That's this red line here. I used 3 different configurations just to see how much change I would see in this lift distribution on those changes. Let me mention those real briefly. One is the wing by itself. No pod, no booms, just the wing. So you can see here, so we got the center section, we got the outer panel, and then we have our little winglets here. And so for the one we're going to talk about, I left off the booms and the pod from the calculations. So that's this red line right here. We do have a fairly flat middle section. When we have a significant change in dihedral, we went from flat to pretty much the elliptical shape. One thing to mention is I'm not quite certain why we're getting this little jog here. It's not significant enough to be an issue, so I've just chosen to ignore it for now. But we do have this interesting dip right here, right where the winglet starts. And then we come pretty close to 0 out here at the edge of the winglet. So I wanted to try to get a little bit better understanding of this significant dip right here where the winglet starts. So the next thing I did was I flattened out the wing. So I completely removed the dihedral here and the dihedral out here. So this was a perfectly flat wing. And that is this kind of greenish line here. So I wanted to see what would happen. Well, as you can see, we now have a pretty much elliptical shape to our lift distribution, even here in the center section and coming out. So the dihedral is causing this very interesting flat spot up here. When it's perfectly flat, we got rid of that. So changes in dihedral clearly cause a little bit of an issue here in the lift distribution. And it almost got rid of this little dip down here where the winglet goes. So we have a very significant change in dihedral for this winglet. As you can see here, especially on the bottom, there's a significant change in dihedral. So that's why we're getting this dip right here. So I just really wanted to try to understand it. I'm not really going to change the shape of the wing yet. And then the last thing I did was I included the pod and the booms. We did that calculation then, and that is this blue line here. So you can see that actually raised the lift just a little bit here in this center section. But other than that, it completely follows this red line, which is why you can't see it out here. It's underneath this red line. So the only thing that the pod and boom did is it raised it just a little bit. Now in the real world, you will typically see a drop in lift any place you have something like the fuselage or a boom or a nacelle attached to the wing. So where the fuselage is, there we should have drop and lift, and where the booms are, we should have drop and lift. But the VLM method that I used to do this calculation has a little bit of trouble dealing with non-flying surfaces. But I would like to point out that the boom and fuselage I am using will not have quite as much of a loss in lift as a typical fuselage or nacelle. It might be a little bit difficult to see, but both the boom and the pod for the pilot don't go all the way back to the back edge of the wing. They actually don't touch where the flaps are. So we shouldn't have quite as much loss of lift for the booms or the pod. So for now, I'm going to go ahead and stick with the lift distribution that we got from OpenVSP. For our calculations, we're going to use this red line. Now you notice this graph on the y-axis, this is in coefficient of lift, the section lift. But we need to get that into lift per foot span so that we can compare it to this estimation that we did before. So I'm going to show you how to use OpenVSP to get the correct coefficient of lift up here on our lift distribution, and then convert that over to lift per foot span, and then we can compare the two graphs. Although we've done it on other videos, let's go ahead and calculate the coefficient of lift of the wing that we're going to need at our V sub A speed, And that'll give us a target to try to get OpenVSP to have a wing coefficient lift that matches what we are going to need. So again, we're going to use our wonderful lift equation. So here's our lift equation down here. Our maximum lift divided by surface area of our wing multiplied by the dynamic pressure. Well, at V sub A, we can calculate our dynamic pressure. That's 55.7 knots. So we take our air pressure multiplied by our velocity in feet per second and then multiplied by 1/2. And that gives us roughly 10.5 for our dynamic pressure. Remember, our N sub 1 is 3.8 Gs. Our maximum lift is 517 pounds. Our wing surface area, 121 square feet. So our maximum load then, when we combine our N and W, is 1,964 pounds. So this is how much load we need to lift. So we plug in our load, our wing surface area, our dynamic pressure, the coefficient of lift we need from our wing then, at V sub A when we're stalling, 1.546. So we want to set the angle of attack of our wing in OpenVSP to give us this 1.546 coefficient lift of the wing. So what we're going to do to set up OpenVSP is we're going to put the wing and the booms and the fuselage in. We're going to hide everything else. And then we're going to go into VSP Aero and we're going to use the vortex lattice method for our method of figuring out a coefficient of lift. We're going to tell it to use the shown geometry in its calculations. And for our flow conditions, I know that that angle for maximum coefficient lift is somewhere between 15 and 20 degrees. So I'm going to use 15 to 20 at 6 points. We're not going to use beta, which means we're not yawing the airplane. So there's going to be 0, 1 point. Mach is roughly 0.08, so we'll use that. And our reference Reynolds number is about 2 times 10 to the 6th, and 1 point there. That's good enough for what we're doing. Now later on, I want to do some calculations with flaps and ailerons. So we're going to go ahead and add flaps and ailerons into our control groupings, but we're going to set those to 0, or actually just leave them out for now. But we'll deal with them again later. In the Advanced tab of VSP Aero, we're going to use the normal file format, not the experimental one. For the stall model, we'll use the Carlson pressure correction, and we will not do any stability analysis, and then we'll launch the solver. Now, I don't really want this to be a tutorial. A tutorial would take a lot of time, and we've already chewed up quite a bit of time in this video. So I'm just going to fast forward through this process. I'll show it to you, but it'll be fast forward. So let's get to it. Let's take a quick look at our results. Let's see if we see anything that looks odd. Looks about right. I do want to mention something on the tessellation that I did here on this wing. It's really overdone. We have far more tessellation than we really need to do our analysis. Now I have the tessellation in here that I have just so that I can make it look cosmetically better. So for an analysis, I could have really reduced this tessellation. So let's talk about the next steps to do. I want to find the two angle of attacks where the coefficient of lift of the wing that OpenVSP is calculated will bracket that coefficient of lift that we want. I will then interpolate to get the correct angle of attack that OpenVSP will give me the same coefficient of lift for the wing. I will then go back and run OpenVSP again at that one single angle of attack. So let's go back and look at that particular coefficient of lift that we wanted. That was 1.546. Now, one of the reasons I didn't want to give a tutorial on what we just did with OpenVSP is that you can find some fantastic tutorials on OpenVSP using the OpenVSP Ground School. I'll put a link down in the description where you can go to the OpenVSP Ground School and learn more about how to use OpenVSP if you don't already know it. But now we're going to talk about something that you may not find in the Ground School, and you may not be able to find any videos about it. When OpenVSP does its calculations, particularly the ones we just looked at, it's going to write out the results to a file that has a .lod extension. What we're going to do is grab that .lod file and load it into a spreadsheet. And then I'm going to save it out to a .ods file format. That's a spreadsheet format. And this LOD file is just a simple text file. And then just because I like to have my information stored up in the cloud, I'm going to take it from this ODS format and load it up into a Google spreadsheet. So let's go ahead and look at that. So here's the file that OpenVSP generated. You can see it has a .lod extension. This part over here is the name that I'm calling the aircraft. This little here is called the degenerate geometry. Let's go ahead and take a look at that in the text editor real quick. So here's what it looks like in a text editor. So all the setup information is right up in here. So calculations at various places along the span of the wing is all these columns here. And then down here at the bottom, what we're really looking at now is these two lines called wing geometry, and right here where you see coefficient of lift. That's what we're interested in right now. Let's load it in a spreadsheet so we can do some calculations on this. Now what I've been using for my spreadsheet on my Linux machine is I use LibreOffice. So let's open with other application. We're going to open LibreOffice Calc. So what you want to do for separators from that text file is specify that everything's separated by spaces, and you want to merge delimiters because sometimes there's multiple spaces. So let's go ahead and do that. And then there's this really long first column. Let's get rid of that. Okay, we now have this in a spreadsheet. Now, another thing I want to point out is all 6 of our calculations are in this file. So this is the first set of calculations at the first angle of attack. In fact, let's just look at that real quick. So the angle of attack was right up here, 15 degrees. So the next one should be 16. So there's angle of attack at 16. So they're all in here. So 17 on through 20 are down here. Okay, now what I want to do is show right here. There's 2 wing geometries. So that's half of the wing, and this is the other half of the wing. So half of our coefficient of lift is going to be on one side, half on the other. Just to aid me a little bit, I'm going to add these 2 together. To do that, I'm going to do equals sum, a left open bracket. I'm going to select those 2 spots. So at 15 degrees, the lift coefficient of our wing is 1.33. So that's less than we want. So I'm going to copy that and come down to the next one. I'm going to plug that there. So 138. Plug this one here. 145. We're still not quite up to our desired coefficient lift. 148. We're getting closer. So the next one is 19 degrees. 1528, and we want 1546. So we're not quite there. So somewhere between 19 and 20. So let's look at 20. Okay, so 19 degrees and 20 degrees brackets the coefficient lift that we want. Now let's do a little interpolation here. So our desired coefficient lift is 1.546. Now this lower one, let's grab that. Do a copy of that, Control C. I'm going to paste that right here. I'm just going to paste the value. And while we're at it, let's just grab this one here and we'll paste him. All right, what's the difference between these 2 values of coefficient lift? So I'm going to do equals that one minus that one. So our 20 degree coefficient lift divided by our 19 degree coefficient lift. So that's a difference of 0.0445. Okay, now what's the difference between this one and our lower one? So that is going to equal this one minus this one. So I want to know what percentage our particular coefficient lift falls between these 2. So this is the difference between those 2. And this one's the difference between the lower one and ours. So that percentage is going to equal our difference divided by total difference equals. So that is almost 40% of that distance here. Now, the difference between our angle of attack is 1 degree. So that means that we need to increase our angle of attack from 19 by 0.089 degrees. So 19 plus that. So we want 19.39 degrees. So let's go back to OpenVSP. Now, instead of those 6 angles, I only need 1 angle. So I'm going to put in that 19.39 degrees. And I'm going to say We don't need any there, and I'm going to say 1 point. Now what we're going to do is run it again and verify that the coefficient lift is where we expect it to be. So let's launch Solver. Okay, our distribution still looks about the same. Let's go look at our LOD file. Here's our LOD file. Let's load it into our spreadsheet. So now we only have one entry in our spreadsheet. Let's come back down to our coefficient lift and let's check that it makes sense. So let's do .546. That's what we wanted. So now I have the correct angle. So what we're going to do next is we're going to look at our coefficient lift at various spots along the wing. And those various spots are this y average. So 0.02 is very close to the root. 0 would be the root. And it goes up to 12.09. If you remember, our semi-span is 12.1. And then it goes to the other side of the wing. So it'd be negative y and goes to minus 12.09. Since our wing is symmetrical, we only need to deal with half of the wing. What I'm going to do now is load this up into Google, and we'll start working in our Google spreadsheets just because I don't want to lose the information. Okay, I've now loaded that ODS file into Google, and by the way, to do that, you come up underneath File, you do Import, and then I did an upload, and I selected my ODS file. There's my ODS file. And in this case, I wanted to load it into a separate sheet in the spreadsheet. So instead of saying create new spreadsheet, I say create new sheet and then hit import data. And so it'll create a new sheet down here with that data in it. So that's something you might do if you're trying to compare different angles of attack. You might load each angle attack in separately. Now what I want to do is come up with that span loading. And that's going to be in pounds per foot. And that foot is along the span of the wing. So that's what I've done out here. Now I also did a calculation of lift by section. So it's pounds of lift per section. And here what I'm talking about by section is each wing. If you remember right, let's bring that up. Here's the overhead view of the airplane. Let's zoom in a little bit here. So you see these lines along here, this tessellation. So you can see these tessellation lines here on the airplane. I did a measurement here from the very center of the wing out to this first tessellation line. It's 0.4. Let's go back and look at those y averages. You see this first y average is 0.2. So it's taking that average of that first tessellation section. The average distance from this tessellation to this tessellation line is that y average. So then I regenerate those tessellation lines. It's just y1 and y2. Take the difference between those, and that's that width of that area. You take that width of the area times the coordinate area. That's a surface area. Then you use your coefficient of lift equation to come up with the lift for that area. So that's what I've done here. So in that area from y1 to y2, we have 40 pounds of lift. And then I sum all that up down here, and we have 1,958 pounds of lift. So 1958. Now what does our lift equation say we should have? Now I did that up here where we have the dynamic pressure, our surface area of the whole wing, multiply the weight and our N1 together to get the total lift that we need. And that comes out with 1,964. So it's about a 6-pound difference between what we calculate using our lift equation here and what we calculate and sum up by all the suction lifts here. So that's not too bad. That's pretty close. But what we really want is the lift distribution in pounds per foot along the span. So basically, we do exactly the same thing, except we don't use the y1, y2. We use the lift equation instead of using our surface area, which would be y1 minus y2 times the chord. We just leave out the y1 and y2 and only use the chord. And that then gives us pounds per foot instead of pounds. So that's going to be this column right here. Let's take a look at this lift distribution and the distribution we got from our previous estimation using the shrink distribution estimation. Okay, so this red line is the shrink, and this blue line is the one that we got from OpenVSP. So as you can see, the shrink estimation is going to have more lift out here towards the tip than the OpenVSP one will. That's going to give us just a little bit more moment at the root. So it's going to be overestimating our moment just a little bit. So we should be able to get a slightly more accurate estimation from our OpenVSP, and we should be able to make our spar caps just a little bit lighter since we won't have as much bending moment out here. Now the next thing to do is to come up with that bending moment and our shear along the wing. Now I had wanted included the wing shear and wing moment in this video, but we've gotten way too long, and so I'm going to do that in the next video. So it'll be 11B. Well guys, thanks for watching. Until next time.